There are a number of different options you can use for generating more complex structures. These are shown under the macros menus as examples, such as a concentrated system of polydispersed spheres, various orientations of cylinders, either randomly or on grids. And these all show as well under the Windows menu, procedure windows, FFT functions that if you look inside these procedure files, it shows details of how these structures are generated, filling the matrix, calculating the Fourier transform, and then saving the results in some way that you can get to them later. This is very good for setting up an automated loop of testing a bunch of structures and doing the calculations, and this can be done without any attention from you. So to try something simple, if we clear that, go to polydispersed spheres and put, say, 300 spheres in, radius 30. We'll just do one pass. Normally you would do multiple passes here because each of these passes fills the spheres into the system, and you get essentially a static snapshot of the system. You're not getting an annealed or averaged structure of the system. So you need to do multiple passes and average them together to get a proper result. So here's the scattering, and it looks like the scattering you would expect from polydispersed spheres. The minimum would be about here, and that's sort of broadened out, and the low Q scattering, it's not obviously evident here, but it is suppressed here due to the fact that the concentration is high. The concentration is about 15%. If you would plot this against a polydispersed spherical form factor, it wouldn't match. You would need the structure factor to account for the volume fraction of about 15% for this to match up. There's other things you can do. Again, clear this out and say put cylinders on a hexagonal grid. This would put cylinders with a radius of about 20, 300 angstroms long, 80 angstroms center to center, with a fill of 10. So we give it a little time to do this, and we can see end on, we have a hexagonal grid. Edge on, we're looking at the cylinders. So if we now do Fourier transform, we get peaks, not surprisingly. Now this Fourier transform here in red would correspond to basically a powder average. If we get a two-dimensional slice, what we see is spots. This is a log representation, this is a linear representation, and of course you get the hexagonal spots you would expect for the hexagonal structure. And if you rotate this structure and change its orientation relative to the x-axis, if you say flip this, oops, did that the wrong way. If you say flip this, then take the Fourier transform, you get a much different result. The powder pattern, is no different because it doesn't matter. It's a powder pattern. If you take the two-dimensional slice, it is very different because now you are looking from the x direction and getting something in the YZ plane. The hexagonal pattern is completely gone. You see tight fringes along the horizontal direction where the length scale is long, wider spaced fringes where the length scale is much smaller, which of course corresponds to the z direction in this case, or the vertical direction. So you can see the Fourier transform is an orientationally averaged value.